The process of converting binary data, which is a sequence of bits, to a digital signal is called line coding. Whenever you have a sequence of bits and you're trying to convert these bits into their corresponding digital signal, the process itself is known as line coding. There are multiple different line coding schemes, which we will be getting into shortly. Now, these line coding schemes have some advantages and disadvantages. To tackle some of the disadvantages that some of these line coding schemes have, we use block coding and scrambling. Now, line coding is always needed whenever you're trying to convert binary data to a digital signal, but block coding and scrambling may or may not be needed. The main focus of this video is encoding binary data using different line coding schemes. However, before getting into that, we are going to familiarize ourselves with some terminologies that are going to come in handy. The first term we'll be looking at is data element, and data elements are what we need to send. These are basically just your binary data. And signal elements are what we can send. So data is what we need to send and signal is what we can send. We can use a vehicle passenger analogy to explain this. Now, data are the passengers and signals are the vehicles. And the vehicle or signal is going to be carrying the passenger or the data. All right, so data is what needs to be carried and signal is what's going to be carrying them. Exactly how a vehicle is going to be carrying the passengers. Just as a vehicle can carry one passenger, it can carry two passengers, it can carry three passengers. Similarly, a signal element can carry one piece of data, it can carry multiple pieces of data, or one piece of data may be carried by more than one signal element. All these scenarios are probable. Now look at the first scenario. You have one signal element and one signal element is carrying one data. Think of the vehicle and in that vehicle only the driver is there, so it's just carrying one person, right? So we're going to be calculating the ratio of data element to signal element, and since one signal element is carrying one data, the ratio is going to be 1. In the next scenario, you have two signal elements carrying one piece of data, right? So one is here represented by this signal. So the ratio is going to be 1 to 2 because two signal elements is carrying one data. Now think of this as a tow truck is carrying another vehicle that's run down and only the driver is driving the tow truck. Okay, so you have two vehicles attached to one another and only one person driving it. Okay, so then if you do a ratio of that, you'll get half. In the third scenario, you have one signal element carrying two pieces of information. So think of a vehicle carrying the driver and along with the driver a passenger. So if you were to do a ratio, you would have 2 to 1 and the ratio would be 2. And now in the fourth figure, you have 4 data elements being carried by 3 signal elements. Okay, so if you were to do a ratio, that would be 4 to 3. Now, data rate defines the number of data elements that's sent in 1 second. So if you relate this to the analogy we used previously, it would mean how many passengers are being sent in 1 second. And signal rate is the number of signal elements sent in 1 second. If you go back to the analogy, this would mean how many vehicles are being sent in 1 second. Also, the signal rate is known as baud rate. It's also called the pulse rate or the modulation rate. So it has a lot of names. Now, our goal in data communication is to increase the data rate while trying to decrease the signal rate. So remember, if there are a lot of vehicles on the road, it creates traffic. More traffic means you're stuck in traffic, and that's not a very desirable scenario. So our goal is to be sending more people, but using lower number of vehicles. So more people in fewer vehicles is going to be our design goal. Now we can calculate data rate by multiplying the signal rate and the ratio of data elements to signal elements. All right, so conversely, we can just write this as signal rate will be equals to data rate divided by the ratio. Let's do a tiny math to test our understanding. Suppose 4 signal elements are being sent in 1 second. If we try to map this to our analogy, 4 vehicles are being sent in 1 second. So the signal rate is 4. Now each of these vehicles is carrying 5 people. Okay? In other words, each signal element is carrying 5 data elements. So if we try to do the ratio to data element to signal element, there are 5 data elements that's being sent per signal element. So the ratio is 5. Then the data rate would be 5 times 4, that's 20. If you think of it simply, there are 4 vehicles and each of these vehicles is carrying 5 people. So the total number of people that's being sent in 1 second is 5 plus 5 plus 5 plus 5, that's 20. And that would be your data rate, the total number of people that's being sent in 1 second, or the total number of data elements that's being sent in 1 second. Another term that we are going to look at is baseline wandering. In decoding a digital signal, the receiver calculates a running average of the received signal power. This average is called the baseline. The incoming signal power is evaluated against this baseline to determine the value of the data element. Now, a long strings of zeros and ones can actually cause a drift in the baseline, which we call baseline wandering. And that makes it difficult for the receiver to decode it correctly. So a good line coding scheme needs to prevent baseline wandering. To explain it simply, suppose this is my data and I'm going to encode 0 as 0 volt and 1 as positive 5 volt. Okay, then my signal would look something like 0, 1, 0, 1. Okay, so a good approximation or a baseline for this would be let's say somewhere around 2.5. Like this would be a good approximation for the baseline, right? So if this is your baseline, then we say that if the received signal is above 2.5 volt, then we call it 1, and if the received signal power is below 2.5 volt, then we call it 0, right? So this is a pretty good approximation. Now, what typically happens is if I had, let's say, 3 ones and 1 0, and if I am calculating a running average, then the baseline would actually get shifted. So what I mean by that is, so suppose this one is 5 volt, 5 volt, 5 volt, and 0 volt, alright? So while I am receiving the signal, if I calculate the running average of this, then the baseline would somewhat be, I just calculated the average of this, so this would be somewhere around 3.75, because I had long strings of ones in it, right? So you see how long strings of one make the baseline shift upwards. And now if I were to one, 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 and 0. Now if if I were to approximate this, then I would say that if the received signal is above 3.75 volt, then that's a 1, and if it's below 3.75 volt, then that's 0. Now this is kind of not a very good approximation for the baseline, because now my baseline has wandered away from a good approximation. Similarly, if I had a long strings of 0 in the data, then my baseline would just shift downwards, right? And that would also ruin the good approximation for the baseline. Now, when the voltage level in a digital signal is constant for a while, the spectrum creates very low frequencies. These frequencies around 0 are called DC component or direct current components, and it presents problems for a system that cannot pass low frequencies. For example, a telephone line cannot pass frequencies below 200 Hz. Okay, so we need a scheme that has no DC component. So if you had a DC component problem, the signal would kind of like be a straight line where the frequency isn't really changing. And this is something that we need to avoid. Another thing to keep in mind is the synchronization between the sender and the receiver. What we mean by synchronization over here is the sender's bit interval and the receiver's bit interval must match. So if the sender is sending data after every, let's say, 1 second, then the receiver should also be reading the data after every 1 second. Now, if that's not the case, then what happens is the receiver may misinterpret data. All right, so the sender's clock and the receiver's clock must match. Now you can send out this synchronization information separately along with the signal, or the signals itself can be self-synchronizing. Now,
self-synchronizing digital signals include timing information in the data being transmitted, and this can be achieved if there are transitions in the signal that alert the receiver to the beginning, middle, and end of the pulse. If the receiver's clock is out of synchronizations, these points can receive the clock. So a good way to achieve self-synchronization is using transition in the signal. Like let's say I will read the data when I am having a transition. For example, suppose I encode this as a 0. So it's a falling edge, and that is when the transition is going to happen, and that's going to help us synchronize the data.